908,947. This was that first genome that was sequenced in a patient from December 2019 in Wuhan. Wuhan, number 1 isolate. So, this is from that sample of lung tissue, and they tell you, when you search for this in NCBI, it tells you all about how it was assembled. So a de novo assembly, and the software they use to assemble it is called MegaHit. So this is a metagenomics assembly software that takes short reads and stitches them back together again. So I think what did you use last time to do your de novo assembly? Velvet? Yeah. Velvet's one that you can use for genomes. It would possibly also work for the data we've got. But MegaHit is being specifically designed for metagenomic data. So it's quick, it is simple, and that's why I use it. But so did the COVID people, so I don't feel too shabby. Okay, it also gives you the paper that this sequence was published in, which is the one we showed earlier. And if you look in NCBI, you might also see some information about different open reading frames and the coding sequences of the virus. So it is indeed 29,903 nucleotides in length. It has a number of open reading frames that create the viral proteins, that create the capsid and the other elements of the virus that do their thing.
And how you find out what it is.
Okay. So you have loaded your reference genome, and you've loaded the COVID genome into the genome portion of IGB. Now I want you to load an alignment track. So could you go back to your IGB browser and go now to the drop-down menu File and select Load from File MN908947_short.bam. Okay, I can see some people have got it loaded. So this is, as its name suggests, an alignment of short reads to the COVID genome. So you can zoom in and out and have a look. Are we having some trouble with some views? Black. Okay. Yeah.
I've never set my life.
Oh, there you go. I am sorry.
So for the Mac users, so if you're a Mac user, you might have trouble seeing what you're seeing. I can see you've made something work there. It may be glitchy as well.
Yeah, if you zoom in too far.
Don't zoom in too far, not for this activity. In week 11, you will get to zoom in as far as you want. But we're just going to have a look at our alignment. I'm going to show you on my computer here. This is my IGB. Okay. Right, so this is what you could be seeing if your Mac is not allowing you to see. This is an alignment here.
No, our virtual machine.
It's that my session fully.
No, mine's still running on actually the session.
So some people crash the IGB, that is interesting. I can't handle.
We worked really hard and freeze.
It just froze.
We zoomed in and I went to click something else and then just
Yeah, I was very zoomed in.
Alright. Yeah. Alright, well, if your IGB's dropped out, try a restart.
went down. Oh, it's working. Oh, shutting down. Oh, it's shutting down. Shut down. Teach a man to fish and he will have patience.
Yeah, the monster just
If I wait for 3 years,
Alright, so we've had some IGV Mac issues and now we've had some crashing issues.
that was on us.
No, that's alright. I mean, I'm glad that your desire was to zoom in because, you know, that's kind of what you want to do when you're looking at this. See what's happening. Let's just look up at this version I have up for you on the screen. This is me viewing IGV on my desktop version, not on the VM version, so it does work this way as well. So what we're looking at here are a bunch of short reads that have aligned to the sequence. The read lengths are around 150 nucleotides in length, and they're all aligning to our reference genome. There are little regions here that have a bit of a line in them, so they're different colour nucleotide to what the reference sequence is. And when you zoom out, you sort of see, or I'm zooming in now, whoops. If you zoom out, you see sort of a general coverage across all the genome, but there are some patches that have a bit of extra coverage for random reasons, usually, especially for viruses. We get quite different alignments than what you would see in an alien genome. Yeah, it's not going to be You can. Okay. So that's what our short read alignment, sorry, will look like. Now, I'm almost scared to ask you to try and load the next track, so maybe we'll just do it on my computer. But I wanted to tell you all about what track you just loaded. So if you could just ignore your IGV woes for a moment. So this sample is downloaded from the Sequence Read Archive, which is a part of the NCBI website. So when you looked up the COVID genome sequence, there's also another section of NCBI where you can actually download data, FASTQ files and that sort of thing. And this is SRR 109-71381. That is the sequence read name of the actual RNA sample that was sequenced from our first patient. If you look this up in NCBI, you'll get a description about its design and who submitted it and lots of other information about it. It's a metatranscriptome sequence of BALF, which is bronchoalveolar lavage fluid of patients. And so this RNA that was extracted was assembled to make this genome. Okay, so these are two matching pairs. We have our FASTQ files that I downloaded and mapped back to the genome, but those FASTQ files were the ones that actually made that genome via de novo assembly as well. So our alignment was similar, like I said, to the BWA thing you did this morning. I used a different software. I used wk4, which is another type of short read aligner. I was asking James earlier, why are we using wk4 and other people use BWA? And we're like, yeah, I don't know. You know, it's sort of like a preference thing, an exposure thing. It's the one I was taught to use, and I've continued using it because it does my job that I needed to do. wk4 is really good for short reads, so sometimes James and I are working with really short reads, like small RNAs, 22 nucleotides in length. So we just use it for our applications, but there are other aligners as well. If you're looking at whole genome transcriptomes, you might use something different like STAR. So I use wk4, but the outcome of a wk4 alignment is the same as the outcome of a BWA alignment. You end up with your SAM file. And so you will then go and use SAM tools to create your BAM and your BAM index files. And it's the BAM file that you load into IGV, and IGV needs the index file too, because it helps to read the BAM file. So from my alignment, I found that only 0.2% of the RNA reads in this sample actually aligned to that virus genome. So what else is going on here? What else is in this sample? If this is where SARS-CoV-2's genome was sequenced from, but less than 1% of the RNA was actually from that virus, what other RNA have we got in this sample? Does anyone want to have a guess? I guess a knowledgeable answer. The patient's RNA, absolutely. So this is a sample taken from a patient's lung. And the virus portion of that RNA is 0.2%. The rest of the RNA is ribosomes, mRNA, non-coding RNA, whatever else RNA was there, maybe some commensal bacterial RNA, other things, just things that are living in the lung, in the BALF. I've learned about BALF today. So that's what we're dealing with often with metatranscriptomics. You've got a heap of RNA, all from everywhere, here, there, and everywhere. If we grind up a bee, we get RNA from all parts of the bee as well as its microbiome. Okay, so I want you to now, don't worry about loading this unless, if your IGV is working fine, I'd like you to load the second file, which is MN908947 Anticon BAM. But if it's not working, I'm going to load mine here for you. Alright, IGV. So load